Alright, so in this video I'm gonna be explaining another important article with the title word-graph2vec, an efficient word embedding approach on word cooccurence graph using random walk technique. This paper in 2023. Word embedding has become ubiquitous and is widely used in various natural language processing tasks such as web retrieval, web semantic analysis, and machine translation, and so on. Unfortunately, training the word embedding in a relatively large corpus is prohibitively expensive. We propose a graph-based word embedding algorithm called word-graph2vec, which converts the large corpus into a word occurrence graph, then takes the word sequence samples from this graph by randomly traveling and trains the word embedding on this sampling corpus in the end. We posit that because of the limited vocabulary, huge idioms, and fixed expressions in English, the size of the density of the word cooccurence graph changes slightly with the increase in the training corpus, so that word-graph2vec has a stable runtime on the large-scale dataset, and its performance advantage becomes more and more obvious with the growth of the training corpus. And their motivation is just about NLP, that when each word in a sentence is like a node in a graph when you do a random walk and go to another node. This is the overall framework of the word-graph2vec algorithm. First, we have a corpus, then we create a random walk sampling. Then we have sampling sequences so that we can do this scriptgram modeling to provide word embedding, which has many applications. An example of graph is shown in figure 2. The source text is an extract of a sentence. In truth, whatever is worth doing at all is worth doing well, and nothing can be done well without attention. And it corresponds to the resulting weighted directed graph, where each vertex represents a unique word and each edge is a cooccurence of two words. So, what is the weight on the edges? The number of simultaneous occurrences of these two words in the text is used as the weight on the edge. A weighted adjacency matrix, W, is used to store the edge weights, and W sub V and X is the weight from node V to node X. So this is weight on nodes. Now it is weighted. So then the second step is sampling word sequences by a random walk. And the sampling time of node V as the starting node are here. This is the number of walks. And this one is the weight of word V. So weight of word V times the total walks is the number of walks. Of course, V is the starting point. And then we have a word-graph2vec algorithm. The algorithm first initializes variables. We scan all the corpus once and build the word cooccurence graph. The adjacency matrix W and nodes weights. The adjacency matrix W and nodes weight have been calculated in this scan. And line 4 is to calculate the transitive matrix using the second transfer probability formula provided by node2vec. So first we are given a processed corpus, the number of sampling n, walk length, context size, and dimension d. And the output of this algorithm is just word-vec representations. So in this step 8, we do skipgram, as you know. So if you don't know skipgram, I've explained it in different videos. There are two ways you can do it. Either skipgram or cbow. And the skipgram, first you give the input is the middle, but the context is the output, and totally opposite to this architecture is the cbow, which we give you the context and you give the output is just the middle word. So we have two approaches for the word-to-vec. Is it skipgram or cbow? Of course, skipgram has much more benefits for many reasons, and glove, for example, is another approach, global embedding. That these are applications of skipgram. And this is the background for skipgram, that you give the input vector and what you output is a probability that word at the random chosen nearby position is, for example, abandoned.